Hello students, welcome back. In the previous video, we went through problem 1a. Now let's go to problem 1b. Same equation and different IVC. Now before going over to this problem, let me make one little comment here. Did I already say this problem is related to population dynamics and epidemiology and things like that? I think I already did. And I even marked it in the original exam as well. So if P is population and B is constant, what do you mean by P0 equals to negative B over 2? What do you mean by negative population? Already this is a bit puzzling. And please remember that. What we do may make a little bit of sense mathematically, but in the end, it should not work as it is. And please remember that, because we're going to have to come back and use that later. Alright. Let's pretend we have no problem about negative population and just go ahead with the problem only through formulation. Alright. Same equation, therefore same general solution. We went through this already and then got this general solution, so we can use it and then plug in the IVC. And P of 0 is negative B over 2. So negative B over 2 is equal to this expression over here, where this expression over here. And the important part is this exponential part. T is becoming 0, so what do you get? We have e to the 0 power. What is e to the 0 power? That's 1. So basically we are getting this equation here. That part drops out and we get b over 1 plus k is equal to negative b over 2. B's cancel out and we solve as k equals to negative 3. Consequently, we have this answer. P of t is b over 1 minus 3 e to the negative at power. So that's the solution of this initial value problem. P of 0 is negative b over 2. Alright. We solve the initial value problem, whether it makes sense or not. Now let's go to the next question. P of t is going to be as t going to infinity or not. Let's do the limit computation. And what do we have? T is going to infinity b over 1 minus 3 e to the negative at. And t is positive infinity, so we have negative already there. So we get e to the negative infinity showing up. What's e to the negative infinity? That's 0, which means this is 0, so that's dropping out, which means this entire part is dropping out. What do you get? B over 1. The answer is B. Oh, we have the same limit as before. Or is it? Well, now you may have to remember a little bit. This is population dynamics we said, and then beginning with negative population, something is not right. Starting with negative population and magically we get positive population, same mature population, just not making much sense here in terms of application. And if this is a valid mathematical model, then math part also have to support that. And here we go. We have this apparent limit computation, but is it really? Well, here we go. In fact, the answer is no, because before the limit going to t going to infinity, the denominator hits 0 first. Set the denominator equal to 0, this thing equal to 0, and solve it. We get this equation and this solution. So t is log 3 over a, which is a positive number. That's when the denominator hits 0. And b is positive number and going here from the left hand side. So what do you get? P is going to negative infinity as t is approaching log 3 over a. Actually, from the left-hand side would have been a little bit more precise expression. Does it make sense? Well, I hope this visualization helps you understand. Let's see. Look at this curve here, especially the left-hand side down here. If we start from population negative b over 2 right here, and then follow the curve, this is solution curve, and population go down to negative infinity. And that one is completely separate from this because it is separated by singularity. So transition from here to there does not appear. Just go to negative infinity and it breaks down. This part over here is completely outside this solution of the interval of definition or interval of solution. Now let's go back to this population dynamics example. And if P is population, then what do you mean by negative population? If P is absolute population, then this is completely impossible. But if P is some base number, say 500,000, plus certain P, it is some excess population, in that case, taking some negative value does make sense. But if the base figure is 500,000, then up to negative 100,000, all right, negative 200,000, all right, but below negative 500,000, then real negative population will take place now, so it does not make any sense. But here, look at this. Look at this picture. We're going to negative infinity. That does not make any sense. So this is indeed a singularity. You see, negative number here is already a bell ringer, but it's not insurmountable problem. But the singularity, that indeed was insurmountable. So that's why the answer was no. We talked about population dynamics and epidemiology and things like those a lot. Let's analyze this a little bit in terms of the differential equation and also the solution. Let's see, I think yeah, okay, all right, let's just copy and paste this thing and then let's analyze it over here. Okay, and then we don't need this anymore. Okay, all right. So if you have this kind of differential equation and assume a and b are positive, then we have this general solution. And let's work out what are the roles of these constant a and b. One observation that you can make is this. Let's see, if P is close to 0, then what we have? Let's see, no, I don't need this part. Yeah, okay. If P is close to 0, then this is approximately equal to, now let's use this over here. Oh, what did I do? Okay. Okay, all right. If P is approximately equal to 0, then that's 0, isn't it? So dp over dt has to be approximately equal to 0. So what does that tell me? The growth is pretty close to 0. Growth is really small when the population is very small to begin with. So if you're talking about some epidemic model, if the infected population is really, really small, then growth is also very small. So as long as you identify the disease and infected people, it's not too difficult to control it. And that's visualization is the left-hand side endpoint of this. Over here, growth is pretty slow here. Let me go a little bit further back. Okay. Growth is really slow here to the left when population is pretty close to zero to begin with. And also makes some common sense. If there aren't that many infected people to begin with, then there won't be as much growth here. On the other hand, population is close to B, then this is what we're going to get. This is P, and then we're going to get B minus B, and that's 0, isn't it? So population is already close to B, which I claim mature population. Then growth is going to be very close to 0. Growth will be very small as well. Let's go to the same picture. This is what we are looking at, the right-hand side. P is already close to the mature population. Then the growth, the derivative, is very close to 0. So as you can see, very flat and getting infinitesimally small. And upon the limit, we're going to get actual 0 limit. So that was the role of B in this population dynamics model. Now, how about the role of A here? Well, if all things are equal, P is appropriate population and then B are fixed, then we are going to get this kind of conclusion here. If A is increasing, if A gets bigger, if A gets bigger, then what happens to dP over dt? This is a bigger value, everything else being equal. Consequently, what do you get? The derivative or growth will also increase. Let's go to that visualization here. And this is based upon A is equal to 1, but let me take different value here. Let's say 0.5, smaller A value. What do you see? You get slower growth. And let's go back to 1, we get this growth. And let's go to 1.5. You can see faster growth. Let's go to 2.5, even faster growth. You see, A is related to how quickly a certain disease is spreading out, or how quickly a certain rumor, like fake news, is spreading out in social media, and so on and so forth. What other things can we see here from this differential equation? How about this part? P times B minus P. We have a quadratic function here, and this P times B minus P hits maximum at, what's the maximum? It hits 0 at P equal to 0, and another 0 at P equal to B, so at half of B, we'll have maximum. And let's see in this model, right in the middle, the slope is the biggest. Let's change this thing a little bit. Let's see, instead of starting from 0, let's change it into, say, 2.0, so that we have over here, maybe a little bit more, 2.5. Okay, and then let's go a little bit more to the right, all right. And then the maximum growth does not take place over here, but around here you can see. And just eyeball it, what do you see? By the symmetry, it's right in the middle, center of 0 and B at 0.5 in this particular case, because mature population here this time is 1. So that's when we have maximal growth. Is there anything more we can get from this differential equation? Well, probably, but I'll leave those two exercises to you guys. And if you want some motivation that how mathematics is being applied to all kind of real world problem, especially a differential equation, look no further than this. This is a kind of equation that appears in chapter 1, but it's this useful already.